So here's our first example. So the problem is this. The problem we're approaching is this. People gain weight when they take in more energy from food than they expend. James Levine and his collaborators at the Mayo Clinic investigated the link between obesity and energy spent on daily activity using data from a study where each of the samples was size 10 and we had 10 who were lean and 10 who were mildly obese but still healthy. And the researchers wanted to address the following question. Do lean and mildly obese people differ in the average time they spend standing or walking? So what we want to do first in our plan is to give a 90% confidence interval for the difference in means, which is the difference in daily minutes spent standing and walking between lean and mildly obese adults. And an examination of the data reveals all conditions for inference can be at least reasonably assumed, right? These are simple random samples. They fit a normal distribution. It's a bit irregular, right? But with only 10 observations, that is to be expected, right? That's a tiny sample size to fit a normal distribution. Typically, we'd want like about 30. So let's take a look at some of the descriptive statistics. So group 1 is our lean group, and group 2 is our mildly obese group. We have a sample size 10. Our mean is in minutes. So lean people spent an average of 525 minutes sitting or standing versus 373.26 minutes. And here's our standard deviation. Again, pretty big standard deviations. So using option 2, using our table, right, I've got degrees of freedom to be 9. That gives me a T critical of 1.88 for a 90% confidence interval. So I take the difference in my means plus the critical T times my standard error, that's all of this. So that's going to be 525.751, that's too many decimal places, minus 373.269 plus 1.833, that's my critical T that we found in our table, times our standard error. That gives me 152.482 plus or minus 73.390, which would give me an confidence interval of the difference being 79 to 225 minutes. It's a little bit different if I use software, because that would give me a higher degree of freedom and a T critical of 1.752 for a confidence interval. It's narrow because option 2 is more conservative, this first one. Let's do another example. So, do college students who have volunteered for a community service work differ from those who have not? Differ how? I guess we'll find out. A study obtained the data from 57 students who had done and 17 who had not. One of the response variables was a measure of attachment to friends. So seeing if people who volunteered were more attached to friends. I don't know how they measured attachment to friends. That would definitely be something we'd want to look for if this was like a research paper. So here are 2 groups. Group 1 is service, group 2 is no service. My sample size, we calculated our sample mean, which was their measure of attachment, and the standard deviations, which looked to be pretty close. So the investigator had no specific direction for the difference in mind, like, oh, there's more attachment or less attachment between the groups. So what they did was they looked at mu1 equals mu2, and just mu1 is different than mu2. So we're going to test the following hypothesis. So we need to calculate a T statistic, one of my favorite things to do. That was slightly sarcastic. So T equals the difference in my means over my standard error. That gives me 105.32 minus 96.82 divided by the square root of 14.68 squared divided by 57 plus 14.26 squared divided by 17. That gives me 8.5 over 3.9677, which gives me a T value of 2.14. So if we use software, right, That gives me a p-value of 0.0415, okay, which is cool. So I feel like I could reject our null hypothesis at the 0.05 confidence level. But let's look at option 2 where we go to the table, which is a little more conservative, right? So I found a sample size of 16. We picked the smaller of the two. So I look at two-sided because this is a two-tailed test because we said not equal to. We're looking for the area in the two tails. Table C shows the p-value between 0.05 and 0.04. So we can conclude that we have pretty good evidence, because our p-value is less than 0.05, that students who engage in community service are on average more attached to their friends.